Welcome back. We now consider some examples on the concept of this chapter, that is on matrix representation of quadratic forms and how to get canonical forms from quadratic forms. Okay, so let's see how this works. The first problem here says obtain the matrix representation of the quadratic form 2x1 squared plus x2 squared plus x3 squared plus 2x1 x2 minus 2x1 x3 minus 4x2 x3. So what makes this a quadratic form? It is because it has these cross product terms. That is what makes this a quadratic form, in that we have a product of two different variables, okay, present there. So if we didn't have anything like this, then this would not be a quadratic form. Okay, and a canonical form is when you have a quadratic form with no cross product term present. Okay, so if this were not present, we would call this 2x1 squared plus x2 squared plus x3 squared a canonical form. Okay, so how do we deal with this? How do we get the matrix representation of this, and what is the meaning of the matrix representation anyways? So basically it is to suggest that this quadratic form, which is 2x squared plus x2 squared plus x3 squared, then plus 2x1 x2 minus 2x1 x3 minus 4x2 x3 could be obtained by this matrix multiplication. Okay, if we have a matrix where we arrange the variables in this form, what are the variables here? X1, x2, x3. So if we arrange them in a matrix, in a row matrix first, that is x1, x2, and x3. Then we multiply, this is x3, we multiply this, okay, matrix by the matrix representation we're trying to get now. Okay, and that will have some entry here. Okay, so because we have three variables, it will be a 3 by 3 matrix. So we don't know the entries for now. We'll come back to that. It will have those entries here and here and here and here. Then we have this here and here and here. Okay, we'll come back to put in what the value should be. Then we also multiply by a column vector of the variables x1, x2, x3. So it is such that when this operation is carried out and the matrix is used in multiplying this out at the end of the day, it will give us this result. It will give us this quadratic form. So the matrix that we should have here is what we call the matrix representation, or the matrix of the quadratic form. And how do we get it? So we just go ahead and follow this approach. What we do is look at it this way, that when we have this first row, just following this order, we have x1, x2, x3. So the first row and the first column, just think about what we have here. Let's say this is row and this is column. The first row and the first column, that is x1 and x1. So think of x1 squared. What is the coefficient of x1 squared? That is 2. So put that here. Okay, this will be this will be first row, second column, so we can think of that as x1, x2. So just pick the first one here, pick the second one here, or pick the first here and pick the second one here. Anyhow you do it, you still have x1, x2. So with that, we look at x1, x2 in the expression. We have 2x1, x2. But that is not the only instance where that will show up, because if we come to this next position here as well, that will be second row, first column. Okay, it will still be x1, x2. Anyhow you want to look at it. Maybe you're looking at it from this end or from this end. It will still give us x1, x2. So because of that, those that are outside this main diagonal, that is, those that are cross product terms, will be split into 2. So because of that, we have 2 to be the coefficient of x1, x2 here. We'll split it into 2 portions. So one of them will come here, that is 1. The other will come here, that is 1. Then we'll go to the next one here. This is third column, first row. Then if we pick the element there, third column, first row, so you can think of that here, that is third and then the first, okay, or the first year and the third year. That is, anyhow you are looking at it, that is x1, x3. So x1, x3 is minus 2. Then we split that also into two portions. That will give us minus 1. Then we know also by the time we come to the third row and first column, we will have the same thing, x1, x3. So that's the second one will come here, x1, x3, okay, coefficients divided into two portions. So we have minus 1 here and minus 1 here, okay. And then right here we'll have second row, second column, that is x2, x2. So what is the coefficient of x2 squared? That is 1. So that will come here. That does not need splitting because that only appears once, okay. So for the next one, we have this to be second row, third column, so that is x2, x3, okay. Whether you're taking it from here, x2, x3, anyhow, you still get x2, x3. And what is the coefficient of x2, x3? You have minus 4. So you split that also into two portions, that will be minus 2. And then here also we have minus 2 because this will also be second column and third row, okay, that is 3, 2. So we still have the same issue here. And then for this, we have third row and third column. That is x3, x3, x3 squared. What is the coefficient of x3 squared? That is 1. So that is what will come here, 1. So this is the matrix representation for this quadratic form. It is always a symmetric matrix. Symmetric in the sense that if you transpose this matrix, it will give you the same result. So the transpose of this matrix is this matrix itself. Okay, think of transposing this matrix 2, 1, minus 1. Then that means you want to make this row become the column here. It is still the same thing here. If you look at this second row also, it is the same thing as what is in the second column. If you look at the third row, it's the same thing as what is in the third column. Okay, so this is a symmetric coefficient matrix, okay, for the quadratic form. And this is what is meant by the matrix representation, if you like, of the quadratic form. Okay, so the process we went through now is unnecessarily cumbersome. Okay, next time you can just say that you have x1, x2, x3, then put another x1, x2, x3, okay, and then put in the matrix. And then with that, when you get to any position here, you know that, okay, let's write that, let's position it better. So let's say this is x1, this is x2, and this is x3. So if you are at any position, you already know that is when you put out all of the variables that appear there, okay, in the quadratic form. When you put them out this way, then when you get here, this is x1 multiplying x1 squared. So that's the only way it appears. There is no other one that can give you x1 squared. So what's the coefficient of x1 squared? That is 2. So you just insert that. x1, x2. So we know this will also give us x2, x1 here. So we have to split that. So the cross product terms have to be split. The coefficient of the cross product terms have to be split into two equal portions because they will appear twice. So because of that, this is 2 and then we'll put in 1. Then x1, x3, we do the same thing. x1, x3 is minus 2. We split that, so we have minus 1 here. x2, x1. x2, x1 is 2, and then we split that, we have 1. x2, x2, that is x2 squared. It appears just once, and the coefficient is 1. And then we have x2, x3 again. x2, x3 is minus 4, split into two portions. That is going to be minus 2. And then for this, we have x2, x3, x1. x1, x3, x3, x2, this is it here. So we split that, that gives us minus 1 here. And then we have x3, x2, x3, x2, that is minus 4, split into two portions, that is minus 2. And then we have x3, 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 that's x3 squared. The coefficient is 1. We have 1 right here. So that is the matrix representation for the quadratic form. It is as easy as that. So this is the matrix that we are interested in. Okay, so we can say that the matrix representation, say A of the quadratic form, is simply 2, 1, minus 1. Okay, 1, 1, and minus 2. Then we have this to be minus 1, minus 2, and 1. Okay, minus 1, minus 2, and 1. Yep, so we're good. So that's how to get the matrix representation or matrix of a quadratic form. Okay, so that is all for this part of the problem. And before we end this lesson, we'll talk about the second part of we'll have a look at another question. Okay, so this says obtain the canonical form of the quadratic form q equals x1 squared plus 24 x1 x2 minus x2 squared. So obviously in this case for this quadratic form, yes, quadratic, it has cross product term, so it is not in canonical form yet. So if we're going to put it in canonical form, it means at the end of the day we will have no cross product term present in that final expression. And how do we do that? We will always start off by getting what we call the matrix representation or the symmetric coefficient matrix for this quadratic form. Just as we did something like that in the first problem. So here now, we get a matrix representation, then we go beyond that to do some more analysis and get the quadratic form. Okay, sorry, the canonical form of this quadratic form. So let's see how that works. So firstly, you can pause the video and give this a try now. Get the matrix representation. At least you now know how to do that from this example. So when you're done, then you return to see what we get. Okay, so for this we have x1 squared plus 24 x1 x2 then minus 6x2 squared. This will be equal to, so for the matrix representation, or we know this itself, the variables are x1, x2, so we can write that as x1, x2. It's going to be multiplying this matrix, so it will be a 2 by 2 matrix since we have only two variables here, x1 and x2. So this will be a 2 by 2 matrix, and then we'll have this to be x1, x2. So follow the same process as before. For the first one, we have x1, x1, that is x1 squared, that is 1. So we have 1 over here. And then for the second one, we have x1, x2. So x1, x2 is here, but that will also be here. So we have 24 divided by 2, that is 12. So we have 12 here and 12 here. Then we have x2, x2, that is x2 squared here. That is minus 6 because it appears only once. Okay, so that means the matrix representation or the symmetric coefficient matrix for the quadratic form is A equals 1, 12, 12 minus 6. Okay, so that's all. So what are we going to do next? We are going to get the eigenvalues of this matrix. That is all. Okay, so to get the eigenvalues of the matrix, we can go ahead and use the eigenvalue problem. Okay, or say we get the characteristic polynomial for this matrix and equate it to 0, then use that to obtain the eigenvalues. That is fine as well. However, this is just a 2 by 2 matrix, and we can just take advantage of the fact that for a 2 by 2 matrix, not a 2 by 2 matrix, even for any kind of matrix, okay, square matrices, of course, for any matrix, the trace of the matrix, what is meant by the trace of the matrix, the sum of the main diagonal elements or entries in the matrix is going to be the same as the sum of its eigenvalues, and the determinant of the matrix is the same as the product of its eigenvalues. So we can take advantage of those two results to actually easily obtain the eigenvalues of a 2 by 2 matrix, because for a 2 by 2 matrix we expect two eigenvalues, and then we know two things about those eigenvalues already, so we can take advantage of that to get the eigenvalues directly without having to write out or get the characteristic polynomial for the matrix. Okay, so for this situation we know, okay, so let us quickly observe that here. Recall that the trace of the matrix A will be equal to the sum of its eigenvalues. So let's say the eigenvalues are lambda 1, lambda 2 that we're trying to get. And then we also know that the determinant of the matrix A will be equal to the product of its eigenvalues, lambda 1, lambda 2, when we multiply them. Okay, so the trace simply means the sum of the principal diagonal or main diagonal elements. So this is 1 and minus 6. When you add them up, that is minus 5. So that is going to give you, that tells you that lambda 1 multiplying lambda 2 is minus 5. Okay, the determinant of this, we can get that with our calculator. We can just multiply it out from here as well. This is 1 multiplying minus 6, that is minus 6. Then minus 12 multiplying 12. 12 multiplying 12 should be 144. Then with that, we have this to be minus 1, 4, 4 multiplying this, that is minus 1, 5, 0. So that means we have this to be lambda 1. So this is lambda 1 plus lambda 2, please. Okay, the addition of these two is minus 5. And then the product of these two is minus 150. Okay, so you can then solve these two simultaneously, or that is not so difficult. You can also think about what are those two numbers which, when multiplied, will give us minus 150, and when added, would give us minus 5. So if you can easily figure that out, fine. If you cannot, then consult your calculator. I mean, go ahead and make substitutions here, solve the resulting equation. You should get minus 15 and 10, okay, by mere inspection, anyways, because minus 15 multiplying 10 will give us minus 150. Minus 15 plus 10 will give us minus 5. Okay, so by that, there is no need to do any more thing. We just say that lambda 1 will be equal to, either of them can come first. So we can say lambda 1 is equal to minus 15 and lambda 2 equal to 10. Okay, so with that, we have the two eigenvalues of this matrix representation of the quadratic form. So the what we call the canonical form of this quadratic form then is simply, so the canonical form, let's say that is P, okay, is simply going to be equal to, so this is just going to be equal to lambda 1 multiplying, let's say y1. We're just using another set of variables now, plus lambda 2 multiplying y2 squared without the cross product terms. That is the equivalent canonical form. Okay. So we know that the arrangements here, the other here is there is no rule to it. So minus 15 can come first, 10 can also come first. Anyhow you write it is fine. So this could be written as minus 15 y1 squared, then plus 10 y2 squared. And again, the choice of variables y1, y2 is arbitrary. I mean, we just choose y1, y2. There's no rule that says we must use y1, y2, but we cannot use x1, x2 that is given, because that will be confusing. It will be suggesting that what we have here is equivalent to having x2, x1, x3 again. That will be a wrong suggestion, okay? Because obviously they are not equivalent. We only say they are equivalent because, okay, there are more details behind this. It has to do with us actually getting what we call an orthogonal diagonalizing matrix, and then getting a substitution from that when inserted here would actually reduce that quadratic form to a canonical form. That is, to get rid of those cross products, the cross product term we have there. But then we don't have to bother about that for a problem like this, because we just need to get the final result. So we know the final result at the end of the day would be the new variable squared multiplying the first um, eigenvalue for the matrix plus the other another variable multiplying the second eigenvalue for that particular quadratic form. Okay, so that is how to deal with it. That means that if we add three variables here, x1, x2, x3, of course inevitably we would have the matrix representation to be a 3 by 3 matrix, and for the 3 by 3 matrix we will also inevitably have three eigenvalues. So in that case, we will have three variables also in our quadratic form, or sorry, in our canonical form representation. Okay, so if we have three variables, for instance, that means we will have a third eigenvalue. So this will just be plus whatever the third eigenvalue is, then multiplying y3 cube or y3 squared. So this is squared, please. Okay, so this is the representation, and of course this can also be in form 10 y1 squared. So I said that the order here is not important. It just depends on whatever order you're keeping to at the end of the day when making your substitution. So this could also have been written as 10y1 squared minus 15y2 squared. So this is still a form. It is still an acceptable canonical form that is equivalent to this quadratic form. Okay, and that is that about that. So you can have your option in this form. That is acceptable. It is okay. You could also say that you want to use another set of variables. Instead of y1, y2, you can say you want to use z1, z2, or t1, t2, or t and s. Whatever set of variables you want to use, that's okay. But what's important is their coefficients and their appearance. So this they're going to be in squared form. That is, we have reduced that to canonical form. There is no cross product term present any longer. Okay, so that is that for that, and that is that for this as well. So either of these can would be an acceptable representation. Okay, and that's all for this lesson. See you in the next lesson as we consider another set of examples on this concept. Thank you for watching.